So is the recording? Yes, it's okay. So welcome everybody. We have the pleasure to have with us this afternoon Savas Zafeiropoulos from Marseille, and he's going to give us a seminar about the determination from lattice quantum chromodynamics of the running coupling constant. I'd like to say just a few words about his career. Savas graduated in physics at the University of Athens, then got the PhD at the Stony Brook University, New York in 2013. After that, he went through postdocs for 6 years in Clermont-Ferrand, France, at the Laboratoire de Physique Corpusculaire, then at the Goethe University in Frankfurt, Germany, then at the College of William and Mary and J. Lab in Virginia, USA, and then back to Germany at the University of Heidelberg. Last year, in 2019, he got a permanent position at the CNRS in France, so passing through a very selective competition, and now he's based there at the Center of Theoretical Physics, Centre de Physique Theorique of the University of Marseille. So his scientific interests include quantum chromodynamics on the lattice, random matrix theory, chiral perturbation theory, non-perturbatory normalization, phase diagram of QCD, graphene, and partonic distribution function. So a quite wide range of interests. As I said before, today he's going to speak us about the determination of alpha strong from the lattice, and I invite him to start his presentation.
Okay, thank you very much, Alessandro, for the very kind and exhaustive presentation of my past. It's always a pleasure to give a seminar at UNICAL. Unfortunately, for obvious reasons, this year we cannot do it in person in Cosenza. So this year we should be happy by doing it online. I guess it's better than nothing. So in the past couple of years, I talked to you about the extraction of pattern distribution functions from lattice calculations, which is one of the two major theoretical uncertainties in, for example, LHC physics. And the other one is the extraction of the strong coupling constant. So this year, just to make a break, we'll talk about the extraction of alpha S with different methods, but always from non-perturbative ab initio lattice simulations. This is work done in collaboration with Philippe Boucaud from Marseille in Paris, Feliciano de Soto from Sevilla, Pepe Rodriguez Quintero from Huelva, and Jorge Segovia from Granada, now also in Sevilla. And this work has been published last year in this article over here. Okay, so this is a brief outline of my talk. I will start with an introduction, then I would give a general presentation of Higgs production, which basically is not the focus of this talk, but I will try to argue why the focus of this talk, the extraction of alpha strong, can play a major role and is going to have a major impact in precision Higgs physics. Then, when I will try to explain to you that it's important to determine alpha strong very precisely, I will show to you how this has been done for the past decades experimentally. I will focus on the extraction of alpha strong from theory calculations, so ab initio calculations of QCD discretized on the lattice. And then I will focus on our calculation, which is the extraction of alpha strong from the two-point Green's functions of QCD, and then we'll conclude. So, the introduction. So the success of the Large Hadron Collider experiments in the exploration and interpretation of many phenomena at the TeV scale are based on experimental advances and, of course, in the progress of perturbative QCD. The discovery of the Higgs actually initiated an era of precision studies for the properties, for example, the couplings of the Higgs. And in these studies, the role of precise theory predictions for the different Higgs observables is absolutely indispensable. I will give a prototypical example that we'll discuss, and this is the gluon fusion cross-section. And this is a prototypical example of theoretical input. It helps the interpretation of the experimental observations, and it enters in the extraction of the Higgs boson couplings, and it's crucial actually in identifying deviation from the standard model predictions in Higgs physics. So there are very, very stringent predictions, and every deviation from these very stringent predictions would be a smoking gun of beyond the standard model physics. The theory predictions for the inclusive cross-sections are unfortunately plagued by significant theoretical uncertainties. So there are scale variations at n and LO, which are indicating that there are missing higher order effects at the order of around 9% at LHC energies. And the theoretical uncertainty was comparable to the experimental uncertainty at the LHC run 1. Hence, it's very clear that with a few more years of data taking, the theoretical uncertainty will be the dominant one, demanding an update of the current theoretical predictions. So we need to update our predictions, and this is a very timely and expedient thing to do in our agenda. Okay, let us have a look at some of these theoretical uncertainties. We'll be focusing on alpha strong, and alpha strong is actually the least precisely known of all the fundamental coupling constants of the standard model. So if one looks up in the particle data group average of, let's say, 2018, would find this value of alpha strong, and it has been extracted with a variety of methods, fitted from experiments. And what is actually curious is that it has an uncertainty that has not been changing throughout the last decade. Actually, even worse, the PDG world average of 2018 had an overall uncertainty that actually doubled the PDG average of 2013, if you compare these numbers over here. So instead of doing progress forward, it seems as if we're doing progress backwards, but this is actually related to the fact that there are many, many uncertainties, and it's very hard to quantify them and take them into account precisely. A plethora of computations of LHC processes depend on actually an improved knowledge of alpha S in order to reduce these theoretical uncertainties. This was explained in this paper. In the Higgs sector, for example, the uncertainty of alpha S is dominating this kind of decays to Charmonia, H to CC bar, to gluon-gluon, branching functions, and also for the H to BB bar partial decays. And all this can have far-fetched impacts, for example, on the stability of the electroweak vacuum, on the unification scale of the interaction couplings, and also new physics scenarios. So some more details on the Higgs production, how alpha strong can be an issue. Let us focus more on this gluon-gluon fusion, which is the dominating process for Higgs production at n and LO QCD. This is how it looks like. So we have a total cross-section, which is a convolution integral of some Barton distribution functions, and these are encoding the long distance physics. These are the non-perturbative contributions, all times convoluted with some short distance perturbative calculations of cross-sections at the partonic level. And here we can see two scales, mu f and mu r. We have the renormalization scale mu r, at which the strong coupling constant is defined, and the factorization scale mu f, which is separating the partonic contribution from the hard part, which is the short distance physics. So they're separating the Barton distribution function, which is the long distance part, to the hard part, which is the short distance physics. So let's start by putting, let's say, our zero gauge, the leading order estimates for such a process. Then if one considers next to leading order QCD corrections, this would increase the cross-section by a factor of 80%. That's a lot. Then if you go to N and LO in QCD corrections, this brings an extra further 25% at 7 TeV. And the convergence is actually expected to improve at 14 TeV, but all in all, one is looking, according to the expert, to a factor of 2 enhancement between LO and NNLO. And then we have a few percent corrections from electroweak radiative loops. Then one can try to evaluate the truncation error, and one is doing so by changing the factorization and the renormalization scale by dividing and multiplying them and changing them in some interval with these factors kappa, 2, 3, 4. This triggers a variation of 10%. Then we have an impact of the finite MB mass in the NNLO loops. It has been quantified as a 3% effect, and 1% effect also is attributed to the scheme dependence of the mass of the P quark. And okay, so we have 3% uncertainty from unknown NNLO electroweak corrections. Then we have an uncertainty coming from the parametrization of the Parton distribution functions, which is inducing 10% errors. And then we have an uncertainty from alpha strong itself. And one can try to let vary alpha strong in such a range, and then we'll see that the 2 to 3% error is going to be propagated to the final calculation. And the situation is not going to change 14 TV. And then, of course, the question that the experimentalists are asking themselves is, can theory help to reduce such an uncertainty on alpha strong? These are the pertinent diagrams for the Higgs production processes that we talked about. We have gluon fusion, associated production with the QQ bar pair, Higgs Stralsund, and vector boson fusion. And here we have a plot for the cross-section of the Higgs production as a function of the Higgs mass from the different processes, and this is taken from the TV for LHC working group. Okay, so what has been done in experiments to determine alpha strong? There's been a lot of work. So, for example, there is work in deep inelastic scattering and in E plus E minus collisions. So when one is extracting alpha strong from deep inelastic scattering processes, one of the main paths is to compare the QCD predictions at NNLO with experimental data at different values of the parameters Q squared and X, and try to fit the structure functions and to extract also along them alpha strong. And data from HERA, Tevatron, LHC have been used for such a task. One can also analyze event shapes of E plus E minus annihilation into hadron states with 2 jets, 3 jets, and so on and so forth, match those to QCD computations at NNLO, and model the hadronization effects by Monte Carlo methods. Already, this is one of the weaknesses of such a method, that one has these hadronization effects, and one is trying to model them in a way which could be satisfactory or not by Monte Carlo methods. Then the event shapes are usually in their jargon characterized by this quantity called the thrust, which is given by this formula. And Pi are the momenta of the hadrons in the final state. For a back-to-back QQ bar pair, tau hat is equal to 1. And for a process with an isotropic emission of particles, we have tau equals 1/2. And QCD predictions at NNLO are used to fit the data on the tau hat distribution and to extract an estimate of alpha S. And this can have actually quite large systematics in the way of incorporating non-perturbative effects in the Monte Carlo or in models to describe tau hat analytically. So there could be a lot of uncertainty in these experimental extractions of alpha S too. Then we have electroweak precision fits. So, for example, one can look at the hadronic decay of the Z boson, and then in this case, however, there's another bias which comes from the assumption that we are working under the strict validity of the standard model in the Higgs sector, which could not be the case if there is physics actually beyond the standard model. And then we have NLO QCD analysis of heavy quarkonia decay, which is also a way to obtain alpha strong. Then an alternative approach, which was very, very famous the past 3 decades, was the measurement of alpha strong via the phenomenological analysis of tau lepton decays. And then one can construct the R ratio, which is given by the decay of tau to tau neutrino hadrons divided by the same thing to electron and tau neutrino. and this is equal to this factor. You have this CKM matrix element, and then here you have electroweak corrections, perturbative contributions, and non-perturbative contributions. Okay, this is a compilation of different experimental results based on deep inelastic scattering experiments and from the other experiments that we talked about before. As you can see, they have quite some big error bars, and there is quite some tension between the different channels. So for all these reasons, it is actually expected and mandatory to see if we can determine also alpha strong from a theoretical calculation. When we are thinking about an ab initio theoretical calculation in QCD, we are thinking of QCD discretized in a space-time lattice and simulated in a supercomputer. How one could actually compute alpha strong. The general strategy is to consider a short distance observable, one scale observable, which has a perturbative expansion in alpha s. Then one can compute the observable on the lattice. And in principle, computing the observable on the lattice has many, many advantages because we have a very systematic way of improving on our accuracy. So we need a lot of resources and a lot of people of doing the analysis, but there is a systematic way of including all the systematic effects. There is no such a thing as an unknown non-perturbative effects and so on and so forth. And then what we do is we compute that observable on the lattice. Then this observable, if it's a good observable, it also has a very high loop perturbative expansion. We fit the two and we can extract alpha s. Actually, there is an advantage compared to the phenomenological experimental extractions of being directly in Euclidean space, because in Euclidean space, perturbation theory for this kind of studies works very well because there are actually less concerns stemming from issues such as hadronization corrections that I talked about before that need to be modeled with some sort of a Monte Carlo process, duality violations. This has been a big issue, for example, because duality violations refer to the failure of the operator product expansion to properly describe the physics on the Minkowski axis, in particular to reproduce the spectral functions, which are the primary experimental data. This was the case for one of the most pristine extractions of alpha s, already back in the 90s from the seminal work of Tony Peak and collaborators on the hadronic decay of the tau lepton. And then there were other sources of systematic errors, such as the neglecting the contribution from higher order condensates. And actually it took to this community roughly 25 years in order to correct even partially for these effects. So what quantities can one look on the lattice? Such quantities could be Wilson loops. We can measure those very precisely on the lattice. They can have a perturbative expansion, and one could fit for alpha strong. Then there are step scaling methods based on the Schrödinger function. We're not going to cover them. This is mainly work of the alpha collaboration. Then one can extract the hadronic vacuum polarization and use that to extract alpha strong. One can extract alpha strong from the eigenvalue density of the Dirac operator. So we have an expansion, a perturbative expansion of the eigenvalue density computed by Theorique and company. And we know that it goes for large lambdas, lambda cube times some corrections in alpha s. We can extract alpha s from this quantity too. And now this brings me to what we're going to talk about in this talk. We can, in principle, extract alpha strong from any QCD vertex that we have in the Lagrangian. So the quark gluon vertex, the 3 gluon vertex, the 4 gluon vertex, the ghost gluon vertex. But then in what comes next, I will try to argue that some vertices are more appropriate than other vertices for some technical reasons. Okay, I would not assume that everybody here is familiar with QCD on the lattice. I just would like to give a very quick primer, just to make sure that everybody can follow. So we start from the Lagrangian of QCD, which has the gluonic part and the fermionic part, and then we discretize the space-time in such a hypercubic lattice. Fermions live on the lattice sides, and the gauge fields live on the links that are the parallel transporters connecting to lattice sides. Pretty much for the case of the gluons, this thing is the beginning and the end of the story. How do one can simulate gluons on the lattice? However, the issues of fermions are kind of a nightmare, putting fermions on the lattice, and one actually can discretize the theory. And if one discretizes the theory, then the infinite dimensional Feynman path integral, the functional integral, is well-defined, very highly dimensional Riemann sum, and this thing obviously can be calculated in a supercomputer like Summit, which right now is the second fastest supercomputer in the world, in Oak Ridge in Tennessee in the United States. And one can simulate this theory with Markov-chain Monte Carlo methods. It's a whole chapter how one performs the simulations, but I just wanted to give you some very vague introduction of that. Okay, this is the starting point, is the Euclidean space path integral with the gauge part in the action and the determinant of the Dirac operator for the fermions. We said the discretization of the gauge part of the action is relatively easy. We just replace the gauge fields with some parallel transporters living on the links. However, the issues with lattice fermions are very complicated. And why is this the case? The case has to do with the so-called doubling problem. When one tries to discretize a Dirac fermion in d dimensions, let's say you start from one Dirac fermion, and then you end up having 2 to the d doublers, unwanted fermions. So let's say you're in 4 dimensions, you want to describe one fermion, and you get 15 extra living in the different corners of the Brillouin zone. But okay, this is something that you don't want, because you want to, let's say, simulate 1 or 2 or 3 or 4, but not having 16 copies for each flavor that you want to study. Actually, there is a no-go theorem formulated many, many years ago by Nielsen and Inomiya, which actually says that one cannot have a discretized version of the Dirac operator which has the correct continuum limit, has no doublers, has perfect chiral symmetry, and also gives a local action. So one would think that this is a very bad dead end of the theory of lattice QCD, and that the story would actually end right there, because you either have to sacrifice locality, or you need to live with those 16 doublers, or you need not having chiral symmetry, or you need not having the correct continuum limit. And actually the first step forward out of this dead end was made many decades ago by Ken Wilson with the formulation of Wilson fermions. So he added to the continuum Dirac operator what is called the Wilson term, which is a discretization of the Laplacian. It looks like a mass term, and like a mass term, it violates chiral symmetry. So from those 4 conditions of the Nielsen-Inomiya theorem, Wilson gave up chiral symmetry, which is explicitly broken in his formulation, and it's only one can only achieve it in the continuum limit. Then there are other formulations, such as the staggered formulation that has been introduced by Kogut and Susskind. This has also advantages and disadvantages. After you do the staggering process, you have 4. You start from 16 copies, 16 doublers. You end up having 4 in the case of staggered, but somehow you have a remaining chiral symmetry, so that's somehow good. And not the full chiral symmetry, but you have a little bit of chiral symmetry. And unfortunately, you want to describe one fermion and you end up having 4. And then one needs to make a dubious move on the lattice to take the 4th root of the determinant to get rid of these unwanted doublers. And there's a lot of discussion and a lot of if one can do such a thing or not. And then there are some formulations, the overlap formulation of Neuberger and the domain wall formulation of Kaplan. This satisfies some sort of, so these have some sort of a lattice chiral symmetry, but of course this comes with the cost, with a very heavy numerical cost. So the cheapest of all those is staggered, then is Wilson. Overlap is probably 2 orders of magnitude more expensive than Wilson, and domain wall is actually something in between because it's also very expensive, but it has almost perfect chiral symmetry, and this is a huge advantage because having an almost perfect chiral symmetry gives small discretization errors. Okay, so somehow we talked about a roadblock, so that one has to face when one puts QCD on the lattice. And the roadblock in developing a lattice theory with good chirality is obviously impossible to get around when one considers anomalies in quantum field theories. And anomalies are extremely crucial in quantum field theory in order to get the correct phenomenology. Remember that anomalies do occur in the continuum, but in a UV cutoff, on the number of degrees of freedoms, there are no anomalies, and the exact symmetry on the regulated action are the exact symmetries of the quantum theory. The only way a symmetry current can have a non-zero divergence is if either the original action or the UV regulator itself explicitly violate that symmetry. And the implication for lattice fermions is that any symmetry that is exact on the lattice will be exact in the continuum limit, while any symmetry anomalous in the continuum limit should be broken explicitly on the lattice, such as the chiral symmetry in the case of Wilson fermions. So what was the idea of Kaplan to have some sort of chiral symmetry? Would like to have a realization of chiral symmetry on the lattice which is, not exact, so we can correctly recover the anomalies, but which actually retains all the good features of chiral symmetry in the continuum, such as protection from additive renormalization of the fermion masses. Actually, here we don't have the time to talk about all the ins and outs of domain wall fermions, but we'll give a very toy model example that one can find in the Lezoux lectures of David Kaplan. There's a curious example in the continuum of such a system which gives a clue on how to achieve this. This example has to do with fermions in an odd dimension which are interacting with the domain wall. In order to be concrete, you can consider a system in 3 dimensions where the fermion has a mass which depends on x2 and switches sign at x2 equals to 0. And imagine as if you have a mass function m x2 divided by modulus of x2. And curiously enough, we'll show that a massless fermion mode exists bound to this 2-dimensional surface, and that it's actually chiral. There is a right-hand mode and not a left-hand one. Thus, the low energy limit of this 3-dimensional theory looks like a 2-dimensional theory of a Weyl fermion with a chiral symmetry, even though we started with a 3-dimensional theory in which there was obviously no chirality at all. And this is what usually happens on the lattice with domain wall fermions. So one starts with a 5-dimensional theory, which actually gives a 4-dimensional theory with almost perfect chiral symmetry properties. Okay, so now let's go back to our calculation. We will apply Lattice QCD as a tool to convert a very precise physical observation, for example, the scale setting of the lattice spacing, in order to extract lambda QCD, and if one knows lambda QCD from renormalization group equations, can know the running of alpha S. We'll be computing QCD Green's functions in lambda gauge, and we'll actually exploit the ghost gluon vertex and renormalized in the so-called Taylor scheme. And our plan is to evaluate the so-called Taylor alpha strong from Lattice QCD with 2+1 domain wall fermions at the physical point. And of course, we're very thankful to the RBC UK QCD collaboration, which gave us those configurations. I explained why do we want to use domain wall fermions, because we are in the precision era. We need to have very good chiral properties, almost perfect. And because if one has very good chiral properties, then the lattice simulation is expected to suffer less the impact of discretization errors. Okay, how can one extract alpha strong from Green's functions? Let's go through the calculation. One needs to fix the gauge. We can go to Landau gauge, and there are MOM type of renormalization schemes which are involving Green functions of quarks, of gluons, and ghosts. So on the lattice, I said that we don't have usually the continuum gauge field A, but we have the parallel transporter U. So in order to recover the continuum gauge field A, we can take the traceless anti-Hermitian part, U minus U dagger, divided by 2I A G naught. This is the gauge field in coordinate space. We can Fourier transform it, and this gives us the gluon propagator. And the gluon propagator has a form factor, a dimensionless form factor times this tensor structure. And one can actually take 3 of those guys and compute the 3 gluon vertex on the lattice, or the 4 gluon vertex. This is how this looks like. It has a more complicated tensor structure. And in the MOM scheme, one can renormalize this vertex with a renormalization constant Z3 to the power -1. This is a renormalization condition. At the subtraction point p squared equals mu squared, this should take the value 1 divided by mu squared. And this is a renormalization condition for the vertex, and one can define a coupling from the 3 gluon vertex. Then one has some lattice data like this. In order to fit well the lattice data, we assume, okay, we have a 4 loops perturbative running, but since the lattice data extend also to low energies, low momenta, where the perturbative running could be somehow dubious, one needs to somehow boost this perturbative running with non-perturbative information, such as calculations through the operator product expansion, which actually, since we're in the fixed gauge, this gets contributions from non-gauge invariant observables, such as the case of the dimension 2 Landau gauge gluon condensate. So we have perturbation theory enhanced with some non-perturbative contributions, and one can fit the lattice data to extract alpha, for example, from the 3 gluon vertex. The 3 gluon vertex is not going to be actually the main point of this talk, because of the fact that when we compute point, noisy it becomes. And actually, I argued in the beginning of this talk that we are in this era of absolute precision for the Large Hadron Collider, so we need the best precision possible. And in order to have the best possible precision with QCD Green's functions, we have to use correlation functions of, let's say, 2-point functions. And we will see that there is a way to do so in a different scheme. And this comes when one looks at the ghost-ghost gluon vertex. So the ghost-ghost gluon vertex in Landau gauge with the UV cutoff lambda. This is related to the gluon propagator, which looks like that, the ghost propagator that looks like that. Then we can define renormalized dressing functions both for the gluons and the ghost. These are the renormalization conditions. This is the amputated vertex. It has more complicated tensor structure. Obviously, it's a vertex, and it renormalizes according to this prescription. But actually, there is an interesting observation. There is a symmetric configuration with k squared equals to q minus k squared equals to mu squared, an asymmetric configuration with the 0 incoming momentum for the ghost. And actually, what happens in this case one can see, and it was shown by Taylor back in 1971, that in that case, the vertex does not renormalize. So the normalization constant of that vertex is equal to 1. And one does not need to compute this complicated object over here with a blob, which is given by this horrible-looking formula. One can actually focus only on the calculation of the gluon propagator and the ghost propagator. And by multiplying those two, one can define a coupling, the so-called Taylor coupling, and it has this very important property that it does not renormalize. And additionally, it only involves two-point functions. We don't have to evaluate the vertex, so it's not noisy. And then the Taylor coupling is related, obviously, in the end of the day, for all these experimental and phenomenological studies, we don't want the alpha strong in the Taylor scheme. We want it in the MS bar scheme because this is what usually people use. But there is a perturbative calculation that connects the two. And this is computed by Theorique, and there are many works by my collaborator Philippe Co and company. And alpha Taylor is related in perturbation theory at 4 loops also to the lambda Taylor parameter. So, okay, how do we compute this in practice in a lattice simulation? So first, we need to fix the gauge. Well, this on the lattice is easier said than done, and I will try to explain you why. So we look at this functional of the links, and then we have to extremize this functional in order to get into the Landau gauge. So in the continuum, Landau gauge means d mu a mu, the 4 divergence of the gauge field equal to 0. And in order to achieve that, we need to minimize this functional by doing gauge transformations. And unfortunately, this is not an easy task because if one looks at the profile of this functional, this looks like a spin glass. It has a lot of minima, local minima, and the problem, it is very difficult to minimize this functional. And therefore, there's a lot of algorithmical development on how to minimize this functional. We will not care about finding the global minimum. We want to fix the gauge at machine epsilon precision, so we need d mu a mu to be smaller than 10 to the negative 16, the modulus of d mu a mu. And the reason is that in order to extract alpha, alpha is a perturbative quantity, so we're not going to care if, for example, a gauge fixing would lead to some problems related to Gribov copies. And then the Faddeev-Popov operator is obtained by deriving this f twice with respect to this trajectory parameter s, which you can see over here, where G naught is the gauge transformation that transforms U into the link U naught at the minimum of f. So this is df ds, a horrible looking quantity, and we have d squared f ds squared, and we arrive at the Faddeev-Popov operator on the lattice. And the inverse of this operator is the ghost propagator. Okay, so then we need to somehow invert this matrix with some procedure, let's say a conjugate gradient type of algorithm. And then we have the ghost propagator, we have also the gluon propagator, and then we are off we go, we can compute alpha. Well, unfortunately, in every lattice calculation or in any quantum field theory calculation, there is a series of limits that needs to be taken because the theory is only defined at a finite box. And then one needs to take the limit of volume of the size of the box going to infinity. The lattice spacing has to go to 0, and so on and so forth. For such a quantity like alpha, going to the infinite volume limit is not the most pressing of all problems. However, correcting for discretization errors is the most important issue. And we're going to see that there are different kinds of discretization errors, and my collaborators in the past 20 years have devised lots of methods in order to correct these discretization errors. Some of these errors actually originate from the fact that by discretizing the quantum field theory on a hypercube, we have broken the SO4 rotational symmetry, which is the Lorentz group in Euclidean space, down to the hypercubic group, H4. So we have only hypercubic rotations. And actually what is beneficial is to average any dimensionless quantity of the lattice Q over the orbits of this group H4. So usually you have several orbits of H4 which are corresponding to a single value of p squared, momentum squared. For example, look at the orbit 1, 1, 1, 1 and 2, 0, 0, 0. They have the same p squared, but then they have different this kind of invariance, p to the 4, for example. So 4 compared to 16 for 2, 0, 0, 0. And one can define 4 types of invariance, P4, P2, P4, P6, P8. And there's been group theoretical studies by my collaborators in the past. I'm sorry not having the reference over here, which have shown that you only have those 4 types of invariance, P2, P4, P6, P8, for any H4 invariant polynomial. And you can have an expansion, and then you expand the function Q in this parameter epsilon, and by assuming that the lattice spacing here is small, you can extrapolate those H4 artifacts away. So you parameterize them explicitly, you fit them, and you get rid of them. However, this is not the end of the story, because there are still O4 invariant lattice artifacts. And if you don't have a very good control of these lattice artifacts, you will never have a very precise sub% or whatever 1% precision on alpha strong. In this article over here, 2 years ago, we showed that beyond perturbation theory, a non-perturbative resummation for the expansion in the coupling at a fixed cutoff would lead a more general expression for these Green's functions, for the gluon or for the ghost. It looks something like that. I just want to show the features. Basically, we were trying to find an ansatz in order to know how to take more efficiently this limit, a squared to 0, because obviously just saying, okay, we'll have a quadratic extrapolation of something else would not be sufficient. We need some theoretical input to model these discretization effects in order to properly extrapolate to 0. And by generalizing one loop result with some assumptions, we postulated that there is such a form for the description of these gluon ghost Green's functions are leading order in a squared. And then there are some scales that pop up, such as the gluon mass. That's actually for someone who's outside of the field, already hearing something about gluon mass would be striking. However, I would like to say that this is a result of the so-called Schwinger mechanism, which is saturating the gluon propagator at p equal to 0. And it actually cures the running coupling of the strong interactions from having a Landau pole at the deep infrared. For those who are not familiar with such a concept, one can have a look at the seminal paper of Cornwall back from 1982. That paper has more than 1,000 citations, reviews by Binozi and Papavasiliou on the emergence of this concept called the gluon mass. So this was the ansatz. I will show you how we tested it in this paper in some quench simulations, and then we applied it in simulations with dynamical fermions in order to extract alpha. But first of all, let's talk a little bit about this weird concept, the gluon mass. So the first thing that everyone could be doing right now that one follows the talk is to go to Google and type gauge boson mass, and then one would see that Google says that so far gluons appear massless, and if they have mass, this would mean that there is some sort of symmetry breaking or Higgs mechanism involved with QCD. So Google is not always correct. And this is taken by a nice talk by Craig Roberts. So gluons are supposed to be massless, but this is very, very true in perturbation theory. We don't know anything about what's happening in the non-perturbative level, actually. We can try to probe the non-perturbative physics or with Dyson Swinger type of analysis. And there's actually no symmetry protecting, in such a case, the 4 transverse gluonic modes like that. And gluons acquire a running mass, which is large at infrared momenta. And this is a prediction for the gluon 2-point function that it's non-zero at finite q square equals to 0. And here there's some papers. These are results for the gluon propagator on the lattice for 4 different values of the lattice spacing from a paper of ours from last year. This is the RGI mass scale for the gluon mass. It's 1/2 proton mass, as you can see. And over here, what is actually very interesting to see is that we have cured very, very well the lattice artifacts. We're talking about 4 different results for the gluon propagator, and you can see that they have a very perfect overlap in a whole range of momenta, from the UV all the way down to the deep infrared. So this is what I meant before, that with the help of a model, we can efficiently extrapolate to 0 cutoff effects. Because if the calculation is contaminated to the cutoff effects, there's no way to achieve high precision. So more about the gluon properties in the IR. In the gap equation for the gluons, in the Dyson-Swinger equations, one can see that we have self-interactions of gluons modify the propagation characteristics of the gluon and partons that are part of the QCD definition. They effectively, therefore, produce dressed gluons which have a mathematical connection to the gluon partons that we are used to, but with wildly different properties. And my collaborator Craig Roberts has been showing this figure and has been advocating a lot about this concept in many, many talks. Okay, so now I would like to show some data from our calculation from QCD 2-point Green's functions. This is the formula that we'll use to fit the lattice data. And some more issues about the QCD 2-point Green's functions. Alpha Taylor is deeply investigated in QCD using both lattice simulations and Dyson-Swinger equations or functional normalization groups. These are continuum non-perturbative methods. The Landau gauge is actually advantageous for solving the Dyson-Swinger equations. And there has been a long discussion on whether the so-called scaling solution or decoupling solution of the Dyson-Swinger equations are effectively realized in confining non-abelian gauge theories. And these issues have profound relations to confinement and the mechanisms of confinement. So there are scenarios of confinement, such as the Kugo-Jima scenario and the Gribov-Zwanziger scenario, and those scenarios are predicting some particular behaviors of the exponents for the gluon and for the ghost propagator in the deep infrared. In the scaling solution, we have the gluon and the ghost dressing function having a power-like behavior, looking like this, implying that the coupling runs to an infrared fixed point in the limit p going to 0. Then there is the decoupling solution, which implies that the gluon propagator has the form of a Yukawa massive particle, and pure Yang-Mills theory would be infrared trivial. Lattice actually prefers the decoupling solution, but there's a lot of fuss about this because the infinite volume problem, and there is a lot of tension between the continuum non-perturbative methods and the lattice. So these are results for the gluon and the ghost propagators, which are the building blocks of Alpha Taylor. These are our results from the Quenst paper of 2018. I just wanted to show you that here we have 4 different values of beta Wilson from 5.6 to 5.9. This is a variation of the coupling from 0.2 Fermi down to 0.09 Fermi. And you can see that we can have a perfect scaling both for the gluon and the ghost propagator throughout the whole range of momenta. So we know what we're doing with the subtraction of lattice artifacts. And then we go to the central part of this talk, which is the extraction of alpha from domain wall fermion calculations with 2+1 dynamical domain wall fermions in the C, directly at the physical pion mass. These are the lattice volumes. This is the lattice spacing. These are the physical volumes. And this is alpha S from the 3 different ensembles that we analyzed, 2 ensembles at the physical point, a third ensemble at the heavier pion mass. We extracted the lambda ms bar being equal to 320 MeV and alpha ms bar at the Z boson pole being equal to 0.1172 with these errors in a remarkably good agreement with the worldwide average of the particle data group. And this is an extraction for the fit for lambda. And this brings me to my conclusions. Alpha S is needed as a theoretical input to all hadron scattering experiments. In some cases, is the largest theory uncertainty, together with pattern distribution functions. There's an intense ongoing experimental and theoretical effort, and it's also important in the search of new physics. We studied the definition of the coupling stemming from the Green's functions of QCD that has a deep connection to continuum non-perturbative methods, such as Dyson's finger equations and the functional normalization group. What comes next? We'd like to go, of course, to finer lattice spacings in order to go to higher and higher momenta. But of course, we would like to do some algorithmic improvements in order to create a step scaling method in order to be able to have a perfect matching with perturbation theory at even higher energies. And many, many thanks for your attention.
Thank you, Savas. We try to clap, although it's not the same effect as we were in person in a seminar room.
Thank you very much.
Okay. Are there questions? Luca, you wanted to start to ask something?
It's me. No, I just clap. Sorry.
Sorry. Okay. No, I have a question, Savas. And how does your determination? I mean, in the current setup, I understand that it can be further improved. How does it compare with other approaches?
With other lattice approaches, well, it's compatible and it will enter flag and so on. It is better than some approaches because of the fact that it's very precise. There's a very pristine extraction of alpha S through the Schrödinger functional and step scaling, and this is what the alpha CLS collaboration has been doing. They have been able to have a sub% precision. We don't have that yet. However, our extraction is kind of a more physical extraction, so we use configurations that everybody's using for normal lattice simulations, and not like those very small configurations for the Schrödinger functional. Additionally, we extracted from a different mechanism. And of course, it's important to have different extractions for the same quantity, because it could be that some methods could have some effects which are giving some systematic errors. So we don't have the best precision, so the best right now is by alpha CLS, but we have a competitive, a very competitive extraction of alpha S, and that's why I think it's interesting to pursue this way of extraction also. And I think that one should extract alpha in many different ways, in the same way as we said before with the experimental extractions. We have different experimental channels that one can use to probe alpha, and because in the end everything should converge. If they don't converge, it could be some issue in the lattice methods, it could be on the matching with the perturbative expansion.
I see. And reducing the error is more a matter of handling with systematic uncertainties, or is it a matter of statistics? So what's the balance?
It's a matter of systematics. Actually, because of the fact that we have 2-point functions, if you look at our plots over here, the statistical error from this part over here is really tiny. However, there are two errors. There is at a certain point you need to match with perturbation. You need to match your lattice observable with perturbation theory. In order to do that, you are safer if you do it at higher energies. Of course, you cannot do it at a very, very high energy because you are bound from your cutoff, which is the lattice spacing, which is related to the maximum. The inverse lattice spacing is the maximum momentum that you can have on the lattice. Finer values of lattice spacing, you can be at a higher value of the momentum, and eventually you can do this matching with perturbation theory in a more safe way. So right now we're using 4-loop perturbative formula, but the lattice spacing is allowing us to have momentum, let's say at 4 GeV. If we could have a lattice spacing that allows us to go up to 10 GeV in the running of alpha, then obviously the matching with perturbation theory would be much more safe. Of course, there are technical issues on the lattice that you cannot do the lattice spacing. It's an exponentially hard problem. You cannot do the lattice spacing smaller than, let's say, 0.04 Fermi. However, one of the best ways of dealing with such a problem is the so-called step scaling method, because in the step scaling method that, for example, has been used throughout the years by the alpha collaboration, the renormalization scale is related to the inverse size of the box. So mu is 1 divided by L. So by making your box smaller and smaller, you are going higher and higher in the renormalization scale. So you can achieve a very high renormalization scale, and you can match to perturbation theory even with 1 loop. So this is something that but of course this means that you need to generate many ensembles in order. Basically, step scaling means to simulate in a discrete way the beta function in order to step up, to go higher and higher, in order to do the matching in a higher momentum, and in order not to have issues from non-perturbative effects in the matching, because this is the most pressing question. When you get the non-perturbative extraction in a hadronic scheme on the lattice, and you match with perturbation theory, how can you be 100% sure that you have no control from non-perturbative effects?
Yes, and another question is actually it was simulated, but what you said right now, you simulated 2+1 fermions on the lattice.
And then
yes,
yeah,
then you
so
try
then
to extrapolate above
to
the
the Z
C-mass.
yeah. So that is exactly. So there are perturbative formulae which are letting compute by Theorique and company, which are allowing you to pass all the flavor thresholds. So ideally, I would like to have 2+1+1. So my collaborators in the past, before I joined this collaboration, they had simulated 2+1+1, and in the paper we have compared with those, but with Wilson fermions, with twisted mass Wilson fermions, and we saw that the passing that charm threshold was apparently, we could do it in a trustworthy way. It also has been a lot of criticism for the work of Alpha CLS that they should be doing 4 dynamical flavors. This is one thing. How do you pass the flavor thresholds in order to go to the mass of the Z boson? And yeah, so Alpha has also shown that apparently it's not affecting their precision that much. But ideally, it would be best to even have a dynamical charm. But my collaborators, before I joined this effort, have done this calculation. We have a plot comparing those alphas in the paper, and we didn't see an effect. Even though you think that it could be an effect, which could be substantial, it seems that it didn't give something that should be troublesome when you overlay our results for alpha from 2+1+1 and alpha from 2+1.
Thank you very much. Are there other questions or comments? Okay, it seems that there is none. So let's thank again Savas, and let me also announce or remind you that in less than half an hour we have another seminar by Francesca Cuteri on, okay, still Lattice QCD on somewhat different subject. So I wait for you back here in half an hour. So thank you again, Savas. It was a real pleasure
Thanks, Alessandro.
to have you with
I
us today.
hope that you liked it and that it was a new topic. And
yes, it's very interesting, and I will, profit by recording to see it again and to go through the more technical issues, which of course they demand some further.
And probably it can stimulate some. The reason I wanted to talk about this topic was that probably stimulate some work over there in UNICAL. I know that you guys have a lot of experience with Wilson loops. It's a very competitive way of computing alpha strong with Wilson loops, like your compatible. The Italians were actually Nora Brampilla and Antonio Vairo. They're trying to extract alpha strong from that formulation. It also has its pluses and minuses, but this is something that one can do. And however, I think that our formalism is interesting because it also has some connections with confinement. So there are all those scenarios about how can one see confinement by looking at the gluon and ghost propagator. Of course, there are very, very strong feelings in this community. There are people who say, okay, that the whole information of confinement can be seen in those objects. Others say that nothing can be seen in these objects. So the statement about the existence of confinement is not obviously something that's depending on the gauge, but when you have fixed the gauge, the mechanism that you see of confinement could be. And obviously very interesting is to see how topological defects can affect those quantities, such as the gluon and the ghost propagator. And anyways, so I hope that everybody liked it. It's kind of awkward giving those online talks because it's a different way looking at your audience and being able to interact with the audience. But we are doing our best to adapt to the circumstances. Okay, thanks.
Thank you
to
again,
everybody,
Savas.
and see you soon. Bye-bye.
Bye-bye.
Take care.
Bye-bye.
Bye. Alessandro.
Just a second. I stopped the recording.